All right, in the last set of notes, 740, we're going to look at periodic trends. So here is just a summary of the different trends. Periodic trends are patterns in the periodic table that make it possible to make predictions about an element's properties. So a lot of trends we see are explained by Coulomb's law. What Coulomb's law is, as the atomic number increases, the nuclear attraction for electrons increases, thus pulling the electrons in more tightly to the nucleus. So increased atomic number equals increased proton number. And then if you think about it, if you are increasing the number of protons, the nucleus is going to get stronger. So the increased strength of that positive nuclear charge means there's a greater attractive force on the electrons. So if we look at one pattern, atomic radius, as we go left to right, it's actually, so left to right, it's actually decreasing. And then as we go down, we would be increasing. So I should say right to left across the table, and down it's going to be increased. So down here in this bottom left corner is the greatest atomic radius. And the definition of atomic radius is 1/2 the distance between the nuclei of two identical atoms bonded together. So it tends to increase as you go down the group. And the reason for this is because the number of electrons increases. So as we go down the group, the number of electrons increases, and also the energy levels increase. So if you think about like every time we go down one of these periods, as we go down here, we're going to add an energy level. And as we're adding energy levels, that means there's more distance between that nucleus and those outer electrons. And so the radius gets bigger. And it increases as you move left. So as we move right to left, it's going to increase as well, because remember, as we go left to right, we're increasing in our protons. So there's fewer protons in each energy level on the left-hand side of the table. So it's going to be looser as far as that attraction between the nucleus and the electrons on the outside. So it's going to get smaller as we go left to right, because more and more protons added each time in the same same energy level means that it's going to pull in that nucleus tighter. Reactivity is our next one. This is a measure of how readily an atom will react. And we've looked at some different trends in reactivity, like if you remember the halogens, as we go down the group, gets less reactive. So like fluorine, for example, we didn't study that one, but like chlorine, which is next, is going to be pretty reactive. And then as we go down, bromine and iodine get less reactive. So atoms tend to react in ways that get them to have the configuration of the nearest noble gas and thus the most stability. So metals increase in reactivity as you move down and to the left. Okay, so down here it's more reactive. But nonmetals are different. So when I was talking about the halogens, that's a nonmetal. And so as we go up and to the right, they're going to be more reactive. So it's like the opposite, metals and nonmetals on each side of the table. Okay, a concept called the shielding effect is when the electrons in the inner energy levels block the attraction of the nucleus to the valence electrons. So those electrons shield the nucleus from being as attractive to those outer electrons. And remember, the outer electrons, or the valence electrons, are the ones that are available for bonding. So it makes the valence electrons even more loosely held. And it tends to increase as you go down a group and the atomic size is increasing. So why is this? The more total electrons an atom has, the bigger it is. The bigger it is, the more inner electrons it has to block the positive attractive force of the nucleus. The more the attractive force is blocked, the greater the shielding effect on the valence electrons, and the more likely they are to react. Electronegativity is a very important one. This one we will see in next unit as well with bonding. So electronegativity is the measure of the ability of an atom in a bond to attract electrons. As we go left to right, it gets more attractive, and as we go up the column or the group, it's going to be more attractive. So actually, fluorine right here is the most electronegative atom. We are going to exclude the noble gases. The bigger the electronegativity, the more strongly the atom attracts electrons. So think about it. Which elements do you think have the greatest electronegativity? Well, I kind of gave that away. If you understand that the ones in this upper right-hand corner, excluding the noble gases, have the greatest electronegativity, which would have the smallest? And what would the noble gases electronegativity be? Well, it would be 0. So as it tends to increase as you move up a group and increase as you move right in a period. And all these trends are kind of overwhelming at first to conceptualize, but you have to take a little time and like really study and write them out so that you can kind of process it. The change, and that's what delta means, the change in En electronegativity is a difference in electronegativity between two atoms, and this is going to determine what type of bonding we have. So the greater the distance, the stronger the electrons are pulled in one direction, so they're not shared as much. As far as ranges to kind of give us an idea of what type of bonds we're looking at, if our change or difference in electronegativity is greater than 2, we're going to consider that to be ionic. Like there's such a big difference and there's such attraction to one of those atoms more so than the other that it actually steals the electrons off of that other atom. So this is going to occur between a metal and a non-metal, where the metal is going to lose the electron because it becomes a cation, and the non-metal is going to take that electron, the anion. If you are less than 0.5, you are going to be considered a covalent bond. There's a lot more sharing, so there's a lot less electronegativity, a lot more sharing. We have 2 nonmetals for covalent. And then we have kind of a subtype of covalent. We have what are called polar covalent and non-polar covalent. So the range between 0.5 and 2 is polar, and polar means uneven. So electrons are unequally shared. And one side is a little more negative because it pulls the electrons towards that side a little harder, and the other is a little more positive. So think about polar, poles, North Pole, South Pole, they're ends, and electrons are going to be pulled towards one side more than the other. And again, we'll see polarity in the next unit. All right. If you want to pause this and try practice predicting bonds based on these ranges, you can, or do it at the end of these notes, but there's a little bit more to go. And that's 742, by the way. Okay, the last little bit here about some other trends, there's what's called ionization energy, and we abbreviated IE. This is the energy required to move one electron from a neutral atom of an element. So it tends to increase as you move up a group and as you move right in a period. And it changes with each electron that is removed. So removing an electron gives an atom a charge. And remember, charged atoms are called ions. We have cations and anions. Oxidation numbers are, I don't use that term too often, but you will see that. It's just charges. So it's the charge of an ion. It's written as a superscript to the right of the symbol. These ions are what will most likely form due to other periodic trends we have seen. Group 1 forms a +1. Group 2 has a +2, and this is depending on how many valence electrons they have. Group 1 will lose an electron to have a full outer shell. Group 2 will lose 2 electrons. We skip our transition metals. They don't follow this pattern as nicely. Group 13, which is group 3A, we call it usually, has 3 valence electrons, so it's going to lose 3 electrons to become a +3. And then group 14 have 4 valence electrons, but like half of them will form a positive charge, half of them will form a negative charge. And that's based on, if you look at group 4A, we have metals and nonmetals in there. Group 5A is going to actually gain 3 electrons, so it becomes 3 minus. Group 6A will become a 2 minus. 7A will become a 1 minus, and there's no charge for noble gases. Ionic radius is the simplest way to compare the size of ions. When atoms become ions, their radii change. So an ionic radius is the radius of a monoatomic ion in an ionic compound. It's monatomic, really. Atoms that lose electrons, like cations, they tend to be metals and they become smaller. And atoms that gain electrons, like anions, tend to be nonmetals. They become larger. They tend to increase as you go down a group, and obviously would be the opposite as you go up a group.